Hello, I'm Philip Myers of PEMY Consulting. On June 10th, I gave a talk at the think tank's 2021 conference about the relationship between natural disasters and chemical and petroleum storage facilities. I'd like to share that with you now. Natech is an odd word that is gaining traction as well as serious consideration among the scientific and industrial communities. The word stands for Natural Hazard Triggered Technological Disaster. Events such as hurricanes, earthquakes, and flooding are Natech initiators, which means that they can trigger a Natech disaster. An important difference between a major incident and a Natech is that the best practices, code standards, and regulations do not really address them or provide guidance about how to cope with them. A Natech can result in destruction of infrastructure, degraded emergency response, and humanitarian crises, as we have all seen from events like Hurricane Katrina or the Texas freeze after Valentine's Day this year. We have a lot to cover about this exciting soon-to-be published API publication 656, so let's get right into it. But before I start, I want to say that this presentation does not necessarily represent the views or opinions of any other organization or person other than myself. Next, some acknowledgements are in order. First, I want to thank the conference organizers. I want to mention that Earl Crochet and I are the co-chairs for the task group responsible for this publication. I would like to thank API and especially Jose Godoy for supporting and promoting the effort. I also want to thank the American Chemistry Council as well as the U.S. National Institute of Standards and Technology, or NIST, for their support and input. Finally, special thanks to Dr. Dan Brooks for getting the Risk Appendix initiated and Dr. Terry McAllister for kickstarting the Resiliency Appendix. I'll try to keep this slide as painless as possible, but we have to get cozy with some terms I will be using. First, think about regular Las Vegas dice. If we toss one many times, then on average, I think you will agree that to get a specific number like 1, that on average you will get a 1 on every 6 rolls of the die. Note that I said on average. Let's call this the mean recurrence interval, or MRI for short. So the MRI for the die is 6. If I toss the die once per year, what would be the annual probability of my favorite number, say a 6? It would be 1/6, right? We will call this number the annual probability of an event. In dealing with Natech initiating events such as earthquakes, you will hear the term annual exceedance probability. It turns out that these exceedance events can be treated the same way that we talked about the Las Vegas dice. Why am I showing you a 100-sided die? All of what we have said about the 6-sided die applies to a die with any number of faces. A commonly used design criterion for flooding is the so-called 100-year flood. It is exactly like the 100-sided die and behaves like a casino die. If you think of every passing year as a toss of the die, then the annual probability of the 100-year flood has a 1% chance of occurring each year and is random, just like the die. But don't be fooled by the small 1% number. Over an exposure period of 50 years, the 100-year flood has an exposure probability of 40%. Over a 100-year interval, the exposure probability is a whopping 63%. Hurricane Harvey smashed into Texas on August 25, 2017. It had an MRI of 1,000 to 2,000 years. Here is a flooded pipe storage yard. This shows a rainfall MRI for Harvey. Note that rainfall is tied to each rainfall gauge so that the MRIs will be different at each location. The flooding caused by Harvey was an event that had a recurrence interval of around 1,000 years. Here is a map showing where Crosby, Texas is. It is in a 500 to 1,000 year MRI region. There was a facility in Crosby, Texas that stores organic peroxides for use in polystyrene cups, plates, kitchen countertops, and other products. This and the next few slides are from the US CSB website and the report on the Artima chemical incident. It has been presented many times and at many conferences, but I want to cover some ground as it specifically relates to Natech. Organic peroxides are unstable at room temperatures, meaning that they can chemically decompose, burn, or explode spontaneously at room temperature. To stabilize it, it must be stored in refrigerated trailers and warehouses, which of course depend on electric power. The flooding of Hurricane Harvey caused loss of power and also knocked out the backup power systems. With no power to provide cooling, the temperature inside the trailers increased and the peroxides began to decompose and generate flames and toxic gases. The toxic vapor spread to surrounding areas. 21 people were injured and over 200 evacuated. Highways that were for emergency response resulted in injuries to responders. Even though the CSB slide does not mention the word Natech, this is exactly what it is talking about. As a result of the previous CSB recommendation, the Center for Chemical Process Safety, or CCPS, developed a very good document that systematically goes into recommendations provided by the CSB. The API 656 task group has relied on it, but API 656 will focus on petroleum storage tanks and provide tools that were not previously available to storage tank owners and operators. On March 11, 2011, what may be the worst Natech disaster in history occurred. It destroyed the Fukushima Daiichi nuclear power plant. The event was triggered by a magnitude 9.0 earthquake, which is the fourth largest earthquake in history. It created a huge tsunami of up to 130 feet in height. Power generation as well as backup power was lost. A third backup seawater cooling system also failed. Without circulating coolant, 3 of the reactors had a meltdown and an evacuation order with a 12-mile radius was enacted. 10 years later, there are still 4,000 people working every day on cleanup and containment. Many evacuation orders are just now being lifted, but there are still 30,000 people in evacuation. Imagine trying to control and mitigate the nuclear power plant disaster scenario with a non-functioning control room without communications or the ability of people to go in or come out. At one point, operations was collecting car batteries to jerry-rig power for basic control functions. The picture really drives home the idea of resilience, which is to ask more than if the system meets design criteria, but what do you do if the design is overwhelmed? And of course, no talk at this conference would be complete without a graphic of our beloved objects, storage tanks. Here the tanks are storing tritium, which is a radioactive isotope of water, which is caused by groundwater seeping through the reactor buildings. There is so much contaminated water that they have run out of tanks and room for it. So a decision was made by the authorities to release it to the Pacific Ocean over time. Luckily, the half-life of tritium is very short and the hazard decays rather quickly with time, but the idea of this release is fiercely protested by many segments of society, as you might imagine, as well as by other countries. So why am I telling you all this? There are a few key concepts that apply to any Natech where industrial plants use large amounts of chemicals, energy, or petroleum. The first is that the threat was underestimated. The design basis tsunami was 3.1 meters above sea level. It was later revised to 5.7 meters. The estimated actual height was 13.1 meters, more than twice the height as the revised design basis. The critical backup power systems were not waterproofed as they were thought to be adequately protected against the 5.7 meter tsunami. There was also evidence that tsunami MRIs for waves exceeding the 5.7 thresholds were as little as 1,000 years. Most important, the principles of resiliency were not applied. TEPCO and the regulators should have considered the 1,000-year MRIs for tsunamis, but they dismissed the evidence. They should have waterproofed the backup power systems as well. This is the third and final Natech I am telling you about today. It was the Great Texas Freeze starting right after Valentine's Day this year. No question about it. This was a very serious Natech incident, and at a price tag of $195 billion, it is by far the most costly disaster in Texas history, even surpassing Harvey in costs. Long periods of below freezing temperatures caused failure of infrastructure. Water lines burst, knocking out water supplies. Natural gas freeze-offs caused losses in power generation capacity, and many roads were impassable. At the peak, some 5 million people in Texas were without power, and some for more than 3 days. 12 million people had no water during this time. Water was contaminated and boiled water orders were issued. Stores ran out of basic items like bread, milk, and eggs. Fire hydrants were unusable. Plumbing systems throughout the state were destroyed by the freeze. Numerous releases of pollutants caused by starting and stopping the fossil fuel infrastructure were reported, including benzene, sulfur dioxide, natural gas, and carbon monoxide. Vaccine shipments were delayed and 1,000 doses were lost. Many lawsuits, including a class action lawsuit, arose from this event. Some utility customers received bills for $10,000 for 1 week of power usage compared to their average $200 monthly bill. The toll in terms of lice was a terrible price. While the official death count was around 150, other sources say it could be 4 or 5 times higher. I'm going to preface the following couple of slides that touch on climate change with good advice from our old friend Alfred E. Newman. This is a NOAA plot developed from at least 12 climate models up to the year 2100. You can see that the best case is 0.2 meters or about 8 inches sea level rise, whereas the worst case is 2 meters. The best case is just a linear extrapolation from 1900 until now, which is about 8 inches. The significance of this is that the flooding impacts on all coastal regions and facilities could be severe. As you know, we have a heavy concentration of petroleum and chemical storage facilities in the Gulf Coast. After Harvey, there was a lot of interest in understanding recurrence intervals for rainfall. Rainfall MRIs are a little tricky because they vary from point to point, so there must be agreement on an area or drainage basin for averaging it. The data in this plot are simulated with the best 6 climate models. The blue dots represent current estimates of MRI based on historical data. The blue dots also represent Harvey's current MRI. The data was validated by historical rainfall data. The red dots represent the extrapolated MRIs at the end of the century based on the worst-case climate scenarios. Instead of Harvey being a 1,000 to 2,000 year event, its MRI drops to about 120 years, or about an order of magnitude more frequent than currently. This plot shows natural disasters that exceed $1 billion. Keep in mind these are count data for type of event. For example, the green is severe storm count and the orange is tropical cyclone count. The bars give the total cost. Notice that on the right that the price tag for 2020 is almost $500 billion. There is a clear increasing trend in the last 4 decades, and many or most of these have produced Natech events. There is a significant body of literature about Natech. It shows that the most significant bad actor in most Natechs is storage tanks. This squares with common sense, since tanks can release large amounts of hazardous and flammable materials. Yet there is little Natech guidance on storage tanks. Professor Jamie Paget of Rice University and colleagues have provided some specific tank studies related to the Texas Gulf Coast. However, there are still many gaps. API 656 will help to fill those gaps. Specifically, there's an appendix on motivating corporate leadership to help decide how, if, and why a Natech might be a worthy pursuit. API 656 contains some engineering design criteria such as how and when to adjust the design case MRI. There's a resiliency appendix. There's a section on risk management where large-scale impacts to infrastructure are possible and how and why most of the current approaches may be insufficient to properly address risk-based decision-making. Here's the organization and layout of the draft as it stands today. The left side is the basic document with various topics. In the middle, we have the appendices. One of the appendices, number 8, is expanded in the right box, which is a set of data sheets. Each data sheet corresponds to one Natech initiator, such as flooding or seismic, and each has useful maps to show where the hazard exists, references for relevant standards, and best practices for that particular hazard. Because of time, I can't talk much about the details of the appendices. Much of the material is new and will allow organizations to develop assessments that were not previously possible. Here are some figures from an appendix on MRIs and probabilistic criteria. It explains what they are, how they are used, and how you can adjust them to suit your individual risk profile. Why should you tweak a design criterion? A good example is the 1968 Flood Insurance Act, which prescribes an MRI of 100 years to a flood zone. I believe this is totally inadequate for critical infrastructure or for refineries. As I said earlier, this means that on average you will be inundated with a 40% chance with an exposure period of only 50 years. For high-value plants or where impacts could damage critical infrastructure, or you simply don't want that kind of risk exposure, you should be using at least 500 or 1,000 or more years. This appendix has all the details for understanding and manipulating MRIs, which is new material not available in the literature. We even have a detailed flooding example that shows how to work with the flood mapping systems by FEMA and the USGS and what kinds of problems there are with the current flood mapping systems. We hope that FEMA and USGS will improve the flood mapping so that the MRI contours are eventually made possible. Currently, they only provide the 100-year and the 500-year contours. In another appendix, we used extreme value analysis to develop a way to determine when and where and how you can exceed the API 10-inch rainfall design criteria for external floating roof tanks at each location where NOAA's precipitation server has data, which is most of the U.S. This work was motivated by Hurricane Harvey. This plot encapsulates tank failure due to buoyancy and lateral forces under varying wind conditions and flooding levels that you would see in hurricanes. It was a challenge to get all of the variables mapped into a single common-sense way of showing the failure envelope. The red line is buoyancy failure, the blue line is sliding failure, and the green line is overturning failure. The three rows correspond to weights of cone roof, dome roof, and open-top tanks, and the columns to different wind speeds. The y-axis is a proxy for the net amount of water that would be required to prevent failure and can be adjusted with a simple formula and conversion to how much product of any specific gravity is needed to stabilize a tank. The information in this appendix will allow tank facilities to quickly and easily risk-rank tanks for failure from flooding and wind forces. It also provides information on how to stabilize them quickly and easily, even for facilities with hundreds of tanks. Yet another appendix is on secondary containment, which is the last barrier against catastrophic releases. We will have an appendix on the many kinds of containment, how to inspect them, how to size them, what the best practices are, as well as how to assess and inspect them. Finally, there will be an appendix on resiliency, which NIST has helped us to develop. If design is the primary defense against failure, then resilience is the insurance policy for bad stuff that happens in spite of our best intentions. So what is left to be done to get API 656 published? We have to draft a few remaining components, the most important being the appendix on secondary containment. Then API decides who to ballot this document to for comment. I am recommending that the CSB, EPA, ACC, NIST, and other API committees. I suspect this will take a good part of the year, and I know that API wants to publish this year if possible. This concludes my talk. Thank you.